Hello everyone and welcome to the channel. I'm Emmanuel, I'm an airline pilot and a member of PMDG's 777 beta team. The feature previews are slowly rolling in on the PMDG forum, and today I want to take the opportunity to have a look at one particular system with you, the hydraulic, landing gear and the brakes. Now, these are some incredibly complex systems on the Boeing 777, but you will be surprised at what depth they are modeled, while the airplane itself still keeps it rather simple towards the pilots. Now, let's go ahead and have a look. This video is based on the post by Matthias Koch in the PMDG forums, but I'll try to shed a couple of backgrounds and a little bit of additional information in it where I see fit. We're going to start with the first picture that we have over here, showing the hydraulic synoptic page of the 777's ICAS system. Now, this one gives you a good idea of which hydraulic system is connected to which primary aircraft system. For example, you can see the left system is connected to some flight controls and the left thrust reverser. The center system is connected to the nose gear and steering, to the main gear and steering, the flaps and so on, and the right-hand system is connected to normal brakes, right reverser, flight controls, etc. Now, each of those hydraulic systems is powered by at least two sources. Now, you can see on the left side you've got the engine-driven pump, and then you also have an electrically driven demand pump that only activates when the system is under a certain load, and the engine pump alone cannot keep up to it. The center system then is driven by electric primary pumps and air-driven backup pumps, which also function as demand pumps, which are being used, for example, during landing gear extension, retraction, during flap extension, etc., and are, of course, audible in the passenger cabin, as they are located roundabout in the area where the wings are, so when you're sitting in that area you will hear them especially loud in the passenger cabin when they're operating. Likewise, the right-hand system is operated by an engine-driven pump and a demand pump, in case there is a stronger than normal demand on the system. Now, if service-based failures are enabled, then you can see on the left-hand side that the hydraulic system needs regular maintenance in intervals of 600 block hours. So every 600 block hours the system needs to be serviced, and if this is not done, then chances are some stuff might break down, as small faults are not detected on time and might rise into bigger problems. Now, you can accelerate this, you can multiply the number of service hours, or rather you can multiply the interval at which you need to conduct maintenance, or if you turn the service-based failures off at all, then this is not going to create too much of a problem. Now, every one of the major hydraulic systems in the PMDG 777 can fail. And of course PMDG does model all that stuff really nicely. Now let's go ahead and go into a little bit of the greater details of the hydraulic systems. Amongst others, they included a complete simulation of the hydraulic system with realistic times for pumps to come online and drop offline, and violating the pump operating limitations will cause the fluid to overheat, resulting in an overheat warning. However, you have to note that the overheat warning light is triggered by a different system temperature than the actual overheating of a pump. And of course, since hydraulic fluid is normally a little bit cooler than the pumps themselves, when the pumps are running, they're going to cool much quicker than if the pumps are not running. For example, it might take approximately 5 minutes to cool an engine motor driven pump to normal temperature in about 5 minutes when a cool hydraulic fluid is being pumped through it, but when it is off and that cooling effect doesn't exist, it can take up to 30 minutes for such a pump to cool down. Now, another interesting fact about the electric motor-driven pumps is that they don't provide all that much pressure. The pressure of the electric-driven pumps is only about 1/6 of that of the engine-driven pumps. So especially on the center hydraulic system, you will often see the air-driven demand pumps being online whenever there is any additional load applied. Now, the left and the right system are also driven by engine-driven pumps, and those are basically directly connected to the engine, and they will always be running when the engine is turning. The pump switch on the overhead, however, is not turning the pump on or off. Instead, the switch controls a solenoid that cuts off the fluid flow to the system, respectively, from the engine-driven pump. Now, that solenoid is held in the closed position by DC power, so the loss of the associated DC bus will cause the solenoid to fail open, thus allowing the engine-driven pump to provide pressure to the fluid on that side of the aircraft again. This could be bad if you had the pump disconnected for a reason, but it also provides some protection against an electric system failure, which might otherwise cause problems. It's really impressive what kind of impressions, or rather what kind of protections are built into aircraft in case of system failures. For example, the engine anti-ice valves have a similar system that in case power is lost, they simply get stuck in the open position so that engine anti-icing is continually applied. Really, really cool stuff there. Now, what's also really good to know is that the hydraulic quantity indications are affected by the landing gear, flaps, spoiler and flight control positions, and of course thermal shrinking. You will notice changes in the hydraulic quantity indicated during the flight as you change the aircraft's configuration, set the parking brake, etc. Now, the hydraulic quantity itself is measured by standpipes within each reservoir, and because the fluid is below the standpipe, you may retain some pressure and functionality even if the system shows no hydraulic quantity at all. So that's really important to keep in mind there. I know that some people will probably be running to the support saying, hey, my hydraulics still work even though I don't have any quantity in there. Well, just because you don't see quantity indicated doesn't mean that there is nothing in the system. And that's exactly how the real hydraulic system works. So let's now look at the 777's landing gear. It is a massive and complex part of the aircraft, and indeed it makes some of the better part of the entire aircraft zero fuel weight. It needs to handle tremendous loads and work flawlessly even when parts of the hydraulic systems fail, and believe me, especially when flight simmers do their first couple of landings, it needs to be able to take a beating. But let's go ahead and go into a couple of the features of the landing gear system. Now, first of all, when the main wheel is being used, or rather when the nose wheel is being used for steering of over 10 degrees, then the main rear two wheels are going to start to turn as well. We can very nicely see it on this screenshot over here, where you can see that the two aft wheels are actually turning in order to minimize stress on the entire landing gear. You gotta imagine that the entire gear over here is longer than a typical car that you might have in your backyard, and if you are turning the entire plane, the forward and the aft wheels would more or less be skidding across the ground. So for that reason, the aft two wheels actually can turn a little bit to provide a little load relief on the entire system. Now, you will notice that the volume of the turbulence caused from the open gear doors in the landing gear base, especially from that of the nose wheel, is going to be modeled in the PMDG 777. So during the landing gear extension and retraction mechanism, when the front gear doors are opening, the same applies to the sounds close to the main gear doors in the cabin, by the way. When those are open, it's actually going to get quite a bit louder, and that's something that is really noticeable. Likewise, when you do an alternate gear extension, the gear doors are going to remain open because there is no hydraulic pressure applied to the system anymore that would retract them. And for that reason, since the doors are going to remain open, it is also going to get quite a bit louder in the cockpit when an alternate gear extension has been done. Now, of course, alternate gear extension is fully modeled in the PMDG 777, including all the effects that it has on the entire hydraulic system and on the supply to the different systems. Now, what's really cool is that in the real airplane there is a little switch located near the gear base that is going to enable hydraulic pressure again to the main gear doors so that they can be closed again. Now, Unfortunately, Microsoft Flight Simulator doesn't enable click spots on the external model, so it was not possible to model that switch right in the location where it actually is. But you can use the maintenance menu in the Universal Flight Tablet or the FMC to reset the gear bay doors so that when hydraulic pressure is being applied again after an alternate gear extension, they can retract again. Finally, we have to keep in mind that the airplane carries a huge amount of energy, and obviously that energy can really heat up the brakes. Now, I'm going to spoil you a little bit with a picture that's going to come later. When the brakes really heat up, they can start to glow. But for now, when we retract the landing gear, while the brakes are like really, really hot, imagine, for example, you do reject the takeoff at a higher speed, you ignore the brake cooling time, and then you take off, retract the gears with the hot brakes going right into the gear bay. That can most certainly cause a wheel well fire warning. Now, the electronic checklist is going to provide you with a checklist to handle that kind of problem, so don't worry about it too much, but chances are you might have to extend the landing gear again to provide cooling to the brakes, and, well, then you can give it a second try if you still have enough fuel. Now, the landing gear trucks included in the 777-300ERs have a unique cantilever function which is fully modeled. That function causes the truck to lock in place during takeoff and use cantilever action to provide additional tail clearance during rotation. You can basically imagine this like the gear is angling upwards, so the aft part of the gear is pushing the entire airplane a little bit upwards, providing additional tail clearance during the takeoff that helps to prevent a tail strike. Of course, that is fully modeled in the PMDG 777. Now, the tail strike prevention and detection system with the animated tail skid is actually modeled if a tail skid is fitted, because that is an optional piece of equipment. In any case, if you do tail strike your 777 and you are going to get the tail strike ICAS message, you got to be very, very careful, because chances are you might have damaged the pressure bulkhead in the aft part of the cabin, and that bulkhead might rupture if the cabin is pressurized, causing a rapid decompression when you climb to higher altitudes. Now, this is obviously a mechanical system, so it can probably still take some stress when the aircraft climbs to higher altitudes, but if you tail striked it and you continue the flight normally, chances are you might be in for an unpleasant surprise at a little later point. Now, one last quick thing over here. The PMDG 777 is one of the few aircraft in Microsoft Flight Simulator where the landing gear actually has its own shadow mask applied to it, so that the beacon is going to cast a correct shadow, something that is not seen very much in Microsoft Flight Simulator. Now, next up, let's go ahead and have a look at the aircraft brakes and the tires. Now, on this picture you can already see that wear and tear on the aircraft tires is modeled. Now, you gotta make a careful check on your walk around to make sure that there is no significant damage to your tires. Now, aircraft tires can take quite a bit of a beating, but nonetheless, you want to be careful that they are not overly worn, otherwise they can fail, especially when they're rotating quickly on takeoff and landing, and that is really not where you want a tire to blow up. But remember though, if you're in the high-speed regime of your takeoff, then a tire failure is not a reason to reject the takeoff unless the ability of the airplane to safely fly is in question. Always remember, it's better to take an airplane into the air and fly it back to have the full runway available for landing it again, other than rejecting a takeoff halfway down the runway or even further down. Those wide bodies can really eat up runway. You're going to see that in the video previews very soon. Now, looking into the entirety of the system, during the walk-around you also have to check the brake wear indicator pins. Now, those are located on the inner part of the landing gear. I'm going to show you all of that in the upcoming tutorials. And they show the wear of the brake disc lining. Now, the further the brake wears down, the lesser brake action it will be able to apply if the brakes are really used to the maximum. Now, auto brakes really cover up for that stuff, but We'll have a little greater look into that stuff when we can actually show you video previews. Now, what's also really nice to see if you look at the images of the landing gear above is that not only the wear on the tires is modeled, but also the dust that you get on the rim. And that's really something. The more the brakes are being used, the more brake dust is being emitted into the air. Talk about emissions and stuff. And that will eventually settle on the rim as well. So when you change your tires using the universal flight tablet, then the rim is normally taken off as a complete part of the system. So you take both the tire and the rim off and put a new one on them. So that is going to be clean as well afterwards. But beware that the brakes are not changed together with the wheels. So if your brakes were used before, they are probably still going to be used now. But all of that stuff can be checked on the walkaround and is visible on the external model of the aircraft, but you can also have a quick look at that stuff on the Universal Flight Tablet, and you're going to see indications of all these systems over there, giving you a quick overview in case you want to simulate your first officer doing the walkaround and telling you about it afterwards. Now, since we already talked about the tires and the wear they accumulate, this is of course based on the original manufacturing specifications and on experience of aircraft operators, and it is going to be simulated live. So depending on the taxi distances, the number of takeoffs and landings, and how heavy or not you apply your brakes, all of that is going to have an influence into how quickly your tires are going to wear down, and of course your brakes as well. So pay careful attention to that. I already told you that the brakes can get hot earlier on, and this picture really shows it nicely. When you overuse those brakes, they are really going to get hot, and eventually they can reach over 700 degrees centigrade on the outside, and on the inside even over 1000 degrees centigrade. Now, obviously they are going to start glowing when that happens, but the temperature spreads slowly. Now, of course, the inner part of the brake, the one that actually is responsible for the braking action, for the friction, that's the part that heats up first. But the sensors are located on the outside of the brake disc, so the heat is slowly spreading through the disc, which causes the brake temperature indication to rise, even for a long time after you have already parked your airplane at a gate. So just because it doesn't show critical right after touchdown doesn't mean that the temperatures cannot become critical later on. If you land at the maximum takeoff weight, which of course is an overweight landing, but the airplane is certified to do that stuff, so if you land right at the maximum takeoff weight and then apply maximum manual braking, you can be very sure that the brakes are going to overheat. That is going to cause the fuse plugs to melt inside the tires, and that is ultimately going to cause the tires to fail. But in normal circumstances, you shouldn't expect your tires just to blow up. There are protections built into that, so-called fuse plugs, and they are going to melt before the rest of the tire starts melting. For that reason, unless there is any damage to the tires, the brakes or the tires are going to just normally deflate without just blowing up. Now, what's also really cool is when you taxi your aircraft, you are going to see that the front brakes are going to cool quicker than the two aft brakes. And that's because the front brakes are subject to air flowing in from the front of the main wheel bogie, while the two aft wheel assemblies are rather shielded from that air flowing in. Of course, that kind of stuff is modeled in the PMDG 777. Now, going on then, the anti-skid system is active in all braking modes and assists with skidding and hydroplanings. Now, each wheel is monitored on its own and controlled independently. To complete the anti-skid system, from wheel speed sensors to regulating valves and control logic, pretty much all of that stuff is modeled. Now, what's also cool is that you can model the brake accumulator pressure under its gauge on the captain's side below the main wheels. If no hydraulic pressure is applied and you modulate your brake pedals, that thing is going to deplete rather quickly. Normally, if no brake pressure is applied, the thing is going to hold for at least 8 hours on the parking brake, but since flight simmers sometimes have their pedals standing right in front of them and rest the feet on them and stuff like that, yes, I am guilty of that, you know, that thing can deplete rather quickly. Now, another interesting fact about the braking system, and this is something that I'm really surprised to read myself in there. I had a chat with a 777 pilot about this a couple of days ago, and he asked me like, do you know that stuff is modeled? And I'm like, I wouldn't know how I can check if it is modeled. And then we agreed, well, it's probably going too far into the details, so we are just not going to bother focusing on that. Well, looking into here, it is modeled, and we can actually see it. So let's go into it. The brake system of the 777 is designed to reject the takeoff close to V1 that can easily be 170 knots in this airplane at 350 tons at the maximum takeoff weight. So obviously the brakes have a huge amount of power available to them. But during normal taxi, far less braking power is required. Therefore, in order to normalize the feeling of the brakes for the pilot, the braking system only uses 4 brakes on each main landing gear during taxi. So one of the pair of wheels is not going to aid in the braking, and the system automatically decides which ones to use based on the brake temperature and a couple of further inputs that go right into it. Now, this does actually show on the brake temperature indicators. The system tries to keep them somewhat equal, but you will see that during certain periods in time, brake application is only going to cause 4 of the brakes on each main wheel bogie to heat up, and 2 of them are not going to be affected because they are not being actively used for braking. Now, the system modulates that, so it may be that the 2 front tires are not applying brakes at a certain period in time, then a short while later they are being used, and the mid tires might not be used. The system decides that automatically based on several sensor inputs. Now, finally, if you're not used to the park and brake function on a modern Boeing aircraft, this one is worth really watching out for. There is an option where you can choose between realistic brakes and simplified park and brakes in the PMDG options in your FMC. If this is set to realistic, then in order to be able to set the park and brake, you need to fully press your brake pedals and then pull the park and brake lever. All the park and brake lever does is to basically fix those brake pedals in place and lock the brake pressure in place that has previously been applied through the toe brakes. So quite a different system there that you need to get used to. When you want to release them again, just press your brake pedals fully in again. That's going to release the lock of the park and brake lever. The lever is going to go back into the stowed position, and then you can take your feet off the pedals again, and the brake pressure is going to be removed and the pedals return into their original position. So that's quite a cool feature that you have over there. Now, finally, to finish this one off, let's talk about the auto brake system for a little bit. Now, a modern airliner's auto brake system, of course including the 777, but the same goes for the 737, for the A320 and so on. Those auto brake systems are designed to achieve a certain deceleration rate, and that deceleration rate is determined by the setting that you make on the lever. Now, basically, Auto Brake 2 provides a deceleration of 5 feet per second squared at a maximum of 1600 psi brake pressure. Auto Brake 3 provides 6 feet per second squared at 1850 psi. Auto Brake 4, 7.5 feet per second squared at a maximum of 2150 psi. And maximum Auto Brake is 11 feet per second squared at a maximum of 3100 psi. Now all of those are going to onset with 0.1 seconds delay after the main wheel spin up is detected if all criteria for auto brake engagement is fulfilled. The only exception to that is the rejected takeoff setting, which is going to apply maximum braking immediately. However, note that maximum auto braking during the RTO scenario is not as much as maximum manual braking when the pedals are pressed completely to the front, but it is recommended to use the RTO auto brakes nonetheless and not override it manually, because though the RTO auto brakes don't apply the absolute maximum amount of braking, they are usually going to be more effective than a pilot braking, because the pilot constantly needs to press the pedals all the way forward, which can be a little bit difficult when you also have to use the pedals to control the steering of the plane on the ground, and when you are being thrown forward into your seat due to the G-forces, you might be thrown a little bit up and down because the runway is not exactly even. So normally the RTO auto brakes provide the best stopping performance, but theoretically the pilot can get a little bit extra deceleration out of the aircraft by going for maximum manual braking. Alright, that concludes our look at the landing gear system and the hydraulics and the brakes of the PMDG Boeing 777. Everything that I just mentioned is of course fully modeled in the aircraft, and as I mentioned, the airplane is designed rather simplistic. You're not going to notice much of the stuff that is going on, but if you take a close look at the indicators in your cockpit, at the synoptic pages, if you listen to the sounds of what is going on around you, then you will notice that all of that is happening in the background, which really provides great immersion in the PMDG Boeing 777. I hope you found this one interesting. Do let me know in the comments below. Let me know if you like this one. Let me know if you think that there are more components to the hydraulic system that you think should be modeled. Now, with all of that, I would like to say thank you very much for watching. I hope you enjoyed this. Be sure to let me know, leave a like, comment and subscribe if you're up for more, and with all of that said, I'm really looking forward to welcome you all again on the next one. In the meantime, if you really love what I'm doing and want me to keep going, I would appreciate a small donation through the Buy Me a Coffee link in the video description below. Thank you for watching and see you all again on the next one.